Thank you very much. Thank you for the invitation to speak here. So indeed, so I'm going to talk about some variations of the sum product phenomenon. So let me start with something very familiar, but I need it for the introduction. So the sum product problem. So what is the sum product problem? We're given a finite set of real numbers, so finite, and we look at its sum set. So its sum set is defined as a plus a prime, where n a prime are in a. And so this is its sum set. And we can also look at its product set, which is a times a prime, where a and a prime are from a. So this is the product set. So a is finite. If it is of size n, we see that we consider here n squared pairs. So in general, if a were random, then we would expect the sum set to be of size n squared. And similarly for the product set, we have here n pairs, of which we take the product. So if a is general, we would expect n squared distinct results here. But if we choose a in a special way, we can make sure that there are many repetitions, and then the sum set can be much smaller. So for example, so if we take a to be the first n integers, then of course a plus a, so all the values I plus j, where I and j are between 1 and n. So very easy to see that this is, maybe I'll close the window. So very easy to see that these are the numbers between 2 and 2n. So 2n minus 1, but roughly n. So even though we expected in general to have n square distinct elements in the sum set, we see that for this specific choice, we have only a linear number, so linear in n, a number of elements here. So this is one example, and if we take a to be a geometric progression, then again, so this time the product set will be small, because all the elements will be of the form 2 to the power of I plus j, where I plus j are between 1 and n. So 2 to so again, linear in n, even though we expected something quadratic in n. And Erdo H and Szab, so they asked what happens if we want, what if we want to choose a such that both the sum set and the product set will be small? And Erdo H and Szab, so they proved that it's impossible. So if a is a subset of R, finite, then one of these sets will have to be large. So the maximum between a plus a and a times a will be at least up to some constant, maybe like to the power of 1 plus some number eta larger than 0. And they conjectured that this should be, so this shows that you cannot have a linear bound on both the sum set and the product set. So sorry, n is the size of a. So this shows that you cannot have a linear bound on both the sum set and the product set, but they conjectured that this should be much larger. So they conjectured that this should be close to 2, very close to 2. So instead of this, I can write 2 minus epsilon, where the constant here will depend on epsilon. And so the result was improved. I think that the best bound, so the current best bound is due to Stevens and Rudnev. And I'm not sure what the number is, but instead of 1 plus eta, it is 4 over 3 plus some constant, 1 over. Okay, so one way to look at this result is saying that we can find A such that somehow it is it fits sums. We can arrange it so that it fits sums, and there are many repetitions with sums. We can find another set A such that it behaves well with respect to products, but when we want to combine this, so want something that behaves nicely with respect to both products and sum, somehow they don't combine well. And so Elekes asked some related question. At least to me, it looks related. So if we have now, so let's look at another way of mixing sums and products. Let's consider polynomials of two variables. F is a polynomial over the reals of two variables. So polynomial is something that takes sums of x and y and products and some sequence of sums and products. And he was interested, so he asked, now for a given f, can we choose a and b such that the image, let me write what it is, if a and b are finite subsets of R, this time we won't need that it will be the same a, so a and b. So the image of a Cartesian product b under f, so f of ab is in a Cartesian product b, can we, so now for a given f, can we choose a and b such that this image will be small, such that this set will be small? So we already saw two examples, right? So we saw that if f is the polynomial x plus y, then we know that we can choose x, we can choose a to be, a and b both to be the first n integers, and then we can make sure that the image of a Cartesian product b under f will be linear in n, right? So I didn't write the question, but the question, can we find AB such that f of AB is small? So this is not a precise formulation, but I hope that given the examples that I just showed, it's clear what it means. So we want somehow to arrange to find a and b such that there are many repetitions. So even though here we consider n squared pairs, if a and b are of size n, then we still get many repetitions and such that this set will be small. So if f of xy is x plus y, we can choose a and b to be an arithmetic progression, then we can see that we have a small image. And another example that we saw is when f of xy is the function x times y, polynomial x times y. And Elekes asked, are there any other examples? So are there? So one can consider some very trivial variations of these two examples. So for example, I can take a polynomial of one variable, h, and consider h of x plus y. So if x plus y is small, then definitely h of x plus y is also small, because h maybe will, it only helps us. Maybe it will cause some distinct values to coincide. But, so here I can also take h of xy. But I can also, instead of x plus y, I can take p of x. Instead of y, I can take p of y. So now we will need to choose the set A such that p of A will be an arithmetic progression, and q of B will need to be an arithmetic progression. And then I have the same phenomenon. So I have some arithmetic progression plus an arithmetic progression. So this is more or less the example of x plus y. And here, again, I can take p of x instead of x and q of y instead of y. And this is essentially the x times y example. And Elekes asked, can one find more other examples, other polynomials of two variables that have this phenomena? That even though we have here n squared pairs, the set is small. So proved. So theorem of Elekes H and onyai shows that no, these are the only examples. So if f is a polynomial of two variables, then for every AB size n, the image will be little omega of n. So more than n. You cannot find a constant and write here at most a constant times n. So little omega of n unless f has one of the forms star. So let's say. So these are the forms star, and sometimes I will call them special forms. Yes, special forms. Okay, so they showed omega of n, and in the later work, so we jointly with Joseph Shoemashi, who is here, and Micha Sharir. What is the right order? Sharir first. Joseph, wait. First. So we reproved this result, and we showed that here, instead of little omega of n, one can show that one can, so f special or f of AB is at least some constant time n to the 4 over 3. So there is some gap. If f is special, one can have something linear in n, and if f is not special, then for any choice AB, we get something much larger than n. Okay, so so we have these results, and all of them have, so in these settings, all the sets are finite, right? A and B are finite sets, and we look at the image and we look at the size of the image. So what about infinite analogs? Can we have some infinite version? Can we look at some infinite A and B and say something about how these polynomials, or even in the sum product problem, how they expand, or what can we say about infinite sets? So for the sum product problem, there is a theorem of Gain. So Hausdorff dimension setting. So I'm not going to define it. You don't need to know what Hausdorff dimension means. I will explain. I'm going to move from this setting to a discretized setting, which I'm going to explain. But Hausdorff dimension setting, so a theorem of Gain says that if we have A is a subset of R or L, and the dimension of, so the Hausdorff dimension of A is alpha, where alpha is between 0 and 1, strictly between 0 and 1. And so again, the sum product result, but with Hausdorff dimension. So the maximum between the Hausdorff dimension of the sum set and the Hausdorff dimension of the product set is at least alpha plus epsilon, where epsilon depends only on alpha. Okay, so this is what Bourdain proved. And this is related to the to Erdo H ring conjecture. So the ring conjecture says that there used to be a conjecture, now it is false. There does not exist a subring of R with Hausdorff dimension strictly between 0 and 1. And Bourgain's result, of course, proves it, because if we had such a subring A, then we can consider the sum set of this subring A and the product set. But since ring is closed under sums and products, then of course A plus A will just be A, and A times A will again be A. So both will have dimension alpha, the same dimension as of A. And so this will be false, right? So if we know this, we know that the conjecture is true. So so this was slightly before Bourgain published his result. He found out that someone else already proved Erdo H conjecture, but with a different method. So proved by
Edgar and Miller.
Edgar and Miller, right? Not, Edgar and Miller, right? Who said Joseph? Were you? Okay. So independent. Okay, and another related conjecture, just to show you that the R works in this infinite setup. So Falconer's conjecture. So Falconer's conjecture says the following. So first, so if we have a subset of R2, let me define its distance set to be delta of P. So this is P. Delta of P to be all the pairwise distances. So the distance between P and Q, where P, Q are from P. So for now, it's just a definition. And the conjecture says that if P is in R2 Borel, and it has Hausdorff dimension 1, then, this is the conjecture, it's not the result, then the dimension of delta of P is 1. And currently the best, so there is a result of Matila, but I want to have my notes in front of me. Okay, somewhere around. Okay, so Matila proved that if the Hausdorff dimension of P is 1, then the Hausdorff dimension of delta of P is at least half. So to make some progress, one wants to show it's larger than 1/2, and indeed, so Bourgain results Bourgain. With some result of Katz and Tau. I'm going to say something about it in a second. So he proved that if dimension of P is 1, then, so he improved the 1/2 to 1/2 plus some constant. So absolute constant. And the way that the very high level strategy is the following. So Katz and Tau had a paper where they formulated all of these conjectures in a discretized version. So they had some discretized formulation, and they showed that all the discretized formulations that they have for several conjectures. So for Falconer's conjecture with 1/2, and for the ring conjecture again with alpha equals 1/2, doesn't matter. But they have these discretized versions, and they show that if one proves the discretized versions, then this implies the Hausdorff dimension versions. And then Bourgain proved the discretized version. Okay, so now I'm going to do something similar for the Elekes theorem that I mentioned before. So we have a polynomial of two variables. Now we have two sets A and B. The dimension is alpha. I want to show that the image is going to be larger than alpha. And the way we proved it is, again, we formulated some discretized version of this statement, and then we proved the discretized version and showed that this implies the Hausdorff dimension version. So let me state, first of all, the Hausdorff dimension version of our results. So this is a joint work with Josh Zahl. And we proved that for polynomial, two variables, real polynomial, so there are two alternatives. Either f is special in the sense that I said at the beginning, so it's essentially x plus y or essentially x times y. So either f is special, what I denoted by star at the beginning, or otherwise it expands. What does it mean? That for every AB substance of R with Hausdorff dimension was alpha, or alpha is 0 and 1, then the Hausdorff dimension f AB is at least alpha plus epsilon, where epsilon depends, so it depends only on alpha and not even on the degree of f or n. Okay, so this is just the analog of the discrete statement that I said in the beginning. And to prove it, as I said, we formulated some discretized versions similar to the ones formulated by Katz and Tao and proved it. So let me now just explain what I mean by a discretized version. So a discretized version, I mean using delta covering. Sorry. So discretized setting. So if we have a subset of RD, we can define its delta covering number to be just the minimal number of balls of radius delta needed in order to cover X. So minimal number of delta balls needed in order to cover. So this is the delta covering number of X. So this is the definition. So now I can think about the previous statements that we had and try to formulate them in terms of the delta covering number, right? So let's think, for example, on the sum product problem. So we have now, usually our sets will be in the 0, 1 interval, something compact. And now we have a set here. We know that its delta covering is something, so it will be delta to the minus alpha. What does it mean? It means it's just, so we should think of delta as 1 over n. Okay, so delta goes to 0, and it's 1 over n. So here it's n to the alpha. Intervals of size delta, so we have some intervals of length delta. So we can even take just the middle point of these intervals, right? If we take the sum of two middle points and we see where it goes, then of course the sum of the intervals will be some other interval around this point, the sum. So it's okay to just take the middle points. And then we can look at this, the regular, usual sum set or product set, right? So we know from the standard sum product theorem that either the sum set or the product set will be large, right? So let's say that the sum set is large. So if we know that the sum set is large of the middle points, so we know that the sums of these middle points will have So the image will have many distinct points. But the question is, maybe there are many distinct points, but maybe they are concentrated in a way such that now the new set, the image set, we will be able to cover it by still a small number of intervals. So there are many distinct elements, but maybe they are close together, so the delta covering number will not increase. And that's the question. Okay. So we can formulate a question here. It turns out that not to give any other condition, this becomes just trivially false. All the formulations becomes false. So we need another assumption. We need somehow the sets not to be concentrated around some small interval or around a point, because then the fact that delta goes to 0, it's trivial to see that we can just trick. It doesn't matter. So if I think of Elekes-R application, if I want to understand the behavior of f, but now if I take all the points around some one point x, maybe f doesn't behave in a typical way around this point. So it's easy to cheat. And later I will show some example, and this example will also explain why here we need a non-concentration assumption. But so we need an extra assumption that says that not only that, so we start with a set that has a certain delta covering number, and we also want to know that it is somehow spread uniformly in the 0-1 interval. And this is maybe the the important thing here is that this is enough in order to imply the Hausdorff dimension version. So this is an extra assumption, but we are okay with it if our motivation, for example, is the Hausdorff dimension version, then we are okay with the extra assumption. Okay, so let me now state the discretized. So my plan is to state the discretized version and then say something about the proof, some kind of a comparison between the proof in the discrete case and what some of the differences that appeared when we try to work in the discretized setting. So statement first. So again, this is a result joint with Josh Zahl. And maybe even have it in my notes. It's a bit technical, but I hope that you will see what's going on. So we have some parameters, not so important for us, but let me just write it. So some kappa, which is at most alpha, is 1. And now we have a polynomial of 2 variables as before. And we want to show that either the delta covering number for any a and b of delta covering delta to the minus alpha is large or f is special, right? This is as usual. So so then either f is a special form as before, the same special forms, or there exists some epsilon, depends on alpha and kappa, and sigma. You can ignore all these parameters. So that if delta is sufficiently small, the following holds. And what holds is this. So we have 2 sets contained in the interval 0, 1. And we know that their delta covering is delta to the minus alpha. So if delta is 1 over n, then we have here something with n to the power of alpha interval. Alpha. And we have some non-concentration assumption on AB that I'm going to write in a second, but the conclusion is then the delta covering number of f of AB is at least delta to the minus alpha minus epsilon. So delta to the minus epsilon is large, right? Delta is small, delta to the minus epsilon is large. And the non-concentration assumption says that delta, that now if we take A and intersect it with some interval, some small interval J, then we cannot have too much of the set A inside this interval. So it's at most the length of J to the power of kappa minus alpha, where J is an interval in length is delta. So if you would try to, and similarly for B, let me not write it for B. So similar. If you would try to write this non-concentration assumption, then you would have something similar, but without, so the sigma will be 0 and kappa will be alpha. This is the natural thing to do. And here, this is some relaxation that we can do. Okay. So this is the statement. Any questions so far? So I want to talk about the proof on this. Okay. So some remarks about the proof. So again, we have a polynomial f of two variables. So I mentioned at the beginning the Elekes-R theorem in the finite setting, right? When A and B are finite sets, and we looked at the image, and I told you that we had some result reproving their Elekes-R result and also improving the exponent. And now when we approach this problem, we tried more or less to follow the strategy that we had in the paper with Joseph Shoemashi and Micha Sharir, and also from another paper with Frank Desu and Micha Sharir and myself. So we had some strategy that we were very familiar with, and we wanted to somehow apply it in this setting. And some of the steps worked the same, and some or different. So now I want to tell you to make some comparison. So we have a polynomial of two variables, and the strategy is to first of all to assume that we will be able to show that it expands. So consider some sets A and B, and now we try to show that f of A and B, f of A B is large. And if we fail, we want to say that we failed because f has a special form. Okay, so we fix. So we have A B subsets. So now I don't know in which setup to write it. So maybe I should write it in the standard, so in the finite setting, and then tell you what's. So now there are finite sets of subsets of R, and we want to show. So we want to show that f of AB is large, right? So now this is the finite setting. So the first step was to use Cauchy-Schwarz in order to move to so use Schwarz to bound. So instead of trying to lower bound f of AB, we will try to upper bound the number of solutions A prime, B prime, B squared, such that f of AB equals f of A prime, B prime. So this is very, very easy to see using Cauchy-Schwarz, but maybe still just to see that it makes sense. So we want to show that the image of f, that f of AB is large, meaning that for many pairs AB, there are many repetitions, right? Because we have n squared pairs, so there are many repetitions. So we expect to see many such quadruples. So many values we will see repeat. So this is the first step. So we want to use it to reduce the problem to upper bounding. To reduce problem to upper bounding this. Okay, so now our goal is to upper bound this. The size of Q. So now our goal is to upper bound the number of such quadruples a prime, b prime, such that f of ab equals f of a prime, b prime. And the idea was to reduce it to an incidence. So reduce to an incidence problem. So what is an incidence problem? So here it's going to be a point curve incidence problem in the plane. So how do we do that? So we have this equation. So we want to know how many such quadruples satisfy this equation. Let's consider the set of curves. So gamma a prime is going to be defined in the following curve. So f of a x equals f of a prime y. So this is an equation. So x and y are the unknowns. This defines a curve in R2, right? So for each pair a prime, I can define such a curve. So in this sense, so set of curves will be gamma a prime or a and a prime Cartesian product A. And I'm going to look at a set of points, which is going to be B Cartesian product P. And the basic property is that B, a point from my point set, B prime, lies on a curve from family. This happens. So what does it mean for B prime to lie on such a curve gamma A prime? So this is the equation for the curve with unknowns x and y. And now I know that B prime satisfy this equation, right? So if we take x equals b and y equals b prime, this equation is satisfied. So this exactly means that f of ab equals f of a prime b prime. So this is called an incidence. So if I have an incidence, this means that I've found such a quadruple in Q. So if I want to bound the size of Q of the set of quadruples, then I can alternatively, or I can from another perspective, I'm trying to bound number of incidences between n, if a and b are of size n, so between n squared curves and n squared points. So there are tools. So in the finite setting, there are tools in order to deal with this problem. And so semi-Erdo is the basic. I didn't plan to give all these details, actually. I'm trying to focus now on the comparison. So I'll try to keep it shorter. So semi-Erdo is an incidence bound in the plane between points and lines. And some generalizations of it, so for example, Pach-Sharir, give similar bounds to families that are more general, and they gave us exactly the bound that we needed. But in order to apply these theorems, we needed to know something about the family of curves and the family of points. We needed to know that no two points are crossed by more than a constant number of curves, and no two curves intersect in more than some constant number of points. And if these two assumptions are satisfied, then we can apply the standard tools standard tools in order to bound number of incidences in the plane, and then we got what we wanted. So the issue was that the challenge was how to identify whether this family of curves and together with this family of points behave as we want so that we will be able to apply these tools. Okay. The real issue was that this defines, it looks like it defines n squared curves, but some curves might coincide, so we might just get the same curve again and again. So this is the thing we wanted to identify. So the last step, so identify cases where incidence bounds cannot be applied. So we knew that there must be such cases that the incidence bound cannot be applied. Why? Just to make sure someone. So how come we knew that for some functions f, the incidence bound will not apply, right? Okay, because we knew that for the special forms, right, if f is x plus y, we knew we didn't expect to get a lower bound on f ab, right? We know that f of ab can be linear when f is a special form. So we knew that sometimes these incidence bounds, we won't be able to apply these incidence bounds. And what we wanted to show is that we cannot apply these incidence bounds exactly when f is a special form. So when I say identify, I mean and prove that this is that this happens if and only if f is a special form, right? So we were able to identify these cases. We got some differential equation. When one solves it, they see that this is so okay. Show that happens only when f special. Okay. So this is roughly the proof in the finite setting. And now when we approach the discretized setting, we wanted to do something similar, and we knew more or less what to expect. So we knew that we want to bound we wanted to move to quadruples. So instead of lower bound in the image of f, we'll try to upper bound the number of such quadruples. So we know that we want to look at this equation. This is just a surface in R4, right? The three-dimensional surface in R4. We know, so we knew that we want to look at the surface, and we knew how the surface should look like and what happens when it is degenerate, when f is a special form. So we understood it pretty well. And so this worked well. So we could do a Cauchy-Schwarz and we could move to this problem. So now in the discretized setting, we want to bound the delta covering of Q, okay, of this of the surface f of x y equals f of x prime y prime intersected with a squared times b squared, and bounded the delta covering number of this. And now instead of the tools from discrete geometry, from the incidence bounds, we had the recent result of Pablo Schmerkin. So replaced by, so instead of the Samedi Trotter and Pach-Sharir, we used the result of Schmerkin that more or less gave this, but it has some assumptions. And we wanted to show that these assumptions apply. And then so this somehow goes together. So this went okay, but there was one issue still here. So when we moved to quadruples, we were able to bound the size, the delta covering number of this set, this intersection, But the problem was that this epsilon that we had depended on f, the degree of f. If f is a polynomial, we also have a result when f is an analytic function, but this epsilon depended on f, and this was an issue. When we wanted to move to the Hausdorff dimension version, we really didn't want the exponent to depend on f. So I want to finish only by giving an example and show you why this will have to depend on. So the epsilon here will have to depend on f, and maybe say one word about how we managed to solve this issue. So an example. So let's take now a specific function. So f of xy will be x plus y plus x squared plus y squared d over 2. So this function is not special. So not a special form. Now let's fix some alpha. And let's choose A and B, and we want A and B to satisfy the non-concentration condition. So actually we can choose them such that they satisfy it in the strongest way that possible. So we want to have delta to the minus alpha. We're going to choose A and B such that the delta covering of A equals the delta covering of B equals delta to the minus alpha. Meaning that we will need delta to the minus alpha intervals of length delta, right? And we want to put them somehow to place them uniformly in the interval 0, 1. So let's just divide the 0, 1 interval into delta to the minus alpha subintervals, equal subintervals, and in each of them we'll place an interval of length delta to the minus alpha, delta, okay. So let's take 1 divided by the number of intervals that we want to have, which is this. So this gives you delta to the alpha. And now, so we will have delta to the minus alpha intervals, each of length delta to the alpha. So delta to the alpha is larger than delta. And now in each such interval, we put a small interval of length delta. So we have exactly delta to the minus alpha intervals of length delta. This is the set, and you can see that it is very uniform, right? So A and B will be more or less, it's going to be something like delta to the delta alpha 2 and to max alpha, delta alpha. So these are only points, not intervals, plus the interval 0 delta. But if you follow the description here, you don't really need to see it to understand. Okay, so these are our sets. And now I want to show that there are many quadruples. So what is the point here? So the point here that here we have x plus y. X plus y, we know it is special. So we know that it will behave like if we have something that looks like an arithmetic progression, x plus y will have a small image, right? Exactly like in the examples that I gave at the beginning. But this part is really ruins the f's from being special, right? This is what makes f non-special. But if I take x and y very small, very close to 0, this thing is going to be smaller than delta. And if this is smaller than delta, then from our perspective, in the discretized setting, we don't really see any differences of length smaller than delta. And then for very small values of x and y, this will behave like x plus y. So I can write the exact, but maybe okay, so let me just, so if I take A squared Cartesian product b squared intersection with 0. So there are constants here, but I'm not writing them because I feel it only distracts from there. So 1 over d. So I only consider the part of I want to bound the number of quadruples or the delta covering of the quadruples, but I only consider quadruples that are at the beginning of that are somewhere at this part. So in the interval 0, delta to the power of 1 over d. So when I do that, you can see that this part, so I have x squared, so the 1 over d becomes 2 over d, and d over 2, so this is roughly delta. So it won't have any effect. So if you do the calculation, you see that this is this gives more than delta to the minus 3 alpha minus 3 over d, I think. So we have some gain here, but this gain will depend on the degree of f, and this is something that we didn't want to have. So okay, one last sentence about this. So in the finite setting, we knew that. So we had this surface in R4, three-dimensional surface in R4, and we knew that even if f is not special, there might be some subvariety of this algebraic variety that doesn't behave as we want, and we could somehow handle it separately. And we try to do the same here, but then we realize that this gives a bound, but this bound depends on the degree of f, and this is necessary. So what we had to do is somehow to look at so some quadruples are problematic, and we know how to identify them here in R4. But in order to avoid this dependency on the dimension here, in this exponent here, we had to somehow identify already in R2 the pairs AB. So now if we have AB, we wanted to identify the pairs A, B, such that A and B are going to participate in some problematic quadruple. So we didn't want to identify these quadruples here in R4. We had to identify them somehow here in R2, already only by looking at AB and not at all the 4 points. And this was new to us, so we needed to find some criteria for this, but we didn't. This solved this issue. You can see also here that it's pretty clear that, so we don't want this part to be small, so we know that the pairs AB that are going to participate in some bad quadruples are going to be near 0, near the place where this is going to be small. Okay, this. Thank you for your attention. This is all I wanted to say.
Let's all unmute and give Orit a round of applause. Does anybody have any questions for Orit?
So maybe one question, Orit.
Yes.
So this was Elekes onyai, and then one should ask the possible generalizations, yes?
You mean Elekes-R?
For example.
So I'm not sure how to answer this. So we tried to look at the application, at least for distances. So you should know it because it's a paper of yours, the distances between 3 points. And there we can prove a discretized version, but we cannot conclude from it a Hausdorff dimension version. So I think that in the discretized setting, there will be an Elekes-R analog. And in the Hausdorff dimension setting, we don't have one. And I'm not sure if it's because some essential reason or just because we didn't obtain it. But so something, for some reason, it becomes, there are some more challenges there. That's what I can say. What other generalizations you went?
Well, there are more, but yes, that's
More variables, for example, this will work. And we have the result for analytic functions because everything is in a compact domain. Then we don't really need the functions to be polynomials.
Okay.
So this is, in this sense, it's more general.
Mm-hmm. And maybe you have a stronger conclusion, like for the ring conjecture. First of all, it implies the ring conjecture also, yes?
We used a result of Schmerkin that uses a result of Bourgain, so probably it's not like we reproved, but what do you mean by stronger version of the ring conjecture? So
that some structures for in the ring, yeah, some structures can't have Hausdorff dimension between 0 and 1. Yeah, okay, I don't know.
I don't know. I don't have, so we didn't try to, I guess. I don't know how to, what it gives, or I don't think it will give anything new there because we use the tools that already rely on, but I'm not sure.
Okay, thank you.
Probably my question is contained in Yoshi's, but I was going to ask how this extends to more variables.
Sorry?
I was going to ask how it extends to more variables. So
okay, I see. So so first of all, we didn't work out the details, so it's not that I'm 100%, but I'm pretty sure that it will work just because I'm familiar with the analog in the finite setting. So in the finite setting, one should obtain separately so I can look at polynomials of more than 2 variables, right? So I can consider a polynomial of 3 variables, example. And this I should prove somehow separately. So in the finite setting, we looked at this, with polynomials of 3 variables, and we have a result. Again, it's joined with Michael Sharir and Frank Desiu, where we look at this. And then this becomes the surface in R4. So before I had f of xy equals f of x prime y prime, and somehow this surface can be replaced. We can do the same analysis, never mind the details, but somehow this is more or less the same as this. So they are more or less the same. And so this is why I think that the 3 variable will work. And then for 4 variables or more, there is a reduction. So this is in the work of myself and then Tzvika Shemtov. So we show that you can reduce the 4-dimensional case to the 3-dimensional one just by checking if you have f of x1, x2, x3, x4. You can, if you fix one of them, let's say we fix x4 equals some number, and then we have a polynomial of 3 variables, and we can check whether if it's the special form or not. You can do that to each of the variables, and then if it's not a special form, so the 4 variables case can be reduced to the case of 3 variables. So I think everything will work, but we didn't include it in the paper, maybe. So I think that these are doable. The more challenging part is the implicit version, where instead of, so I didn't mention the Elekes-R result. So instead of z equals f of xy, one consider f of xy z equals 0. So in the finite setting, this is more or less the same. In the discretized version, somehow we had some technicalities that I'm not sure even now if to say if we think they are essential or they're just technical. Actually, it's not organized good enough. Did it answer that?
Okay, thank you.